Hello, this is a video lecture for the Pattern Recognition and Decision-Making Processes course offered at Purdue University. This specific video covers the convergence of the maximum likelihood estimator over multiple trials of data. It is a tie-in to Section 9, the parametric density estimation methods, for those of you enrolled in the course. For those of you who aren't in the course or aren't familiar with the subject, we're going to briefly review the maximum likelihood estimator before continuing into the main topic for this video. So begin by going over the assumptions involved when using MLE. The first assumption is rather obvious, is that the samples that you have that you're going to be using for the estimates have to be taken independently and over identically distributed observations. This pretty much means use the same density function when you're taking your data. If you use different ones and try and combine them, you're going to get nonsense. It's fairly straightforward, but it's necessary to mention. The second main assumption deals with the unknown probability density that we're trying to estimate. We're going to refer to this as F0, and the interesting thing about F0 is it has to belong to a family of distributions. For the purposes of this video, we'll be dealing with only normal distributions. They're easy to work with and easy to represent, and you can still get powerful conclusions from them. So for this assumption, F0 has to be a normal distribution. We don't know the specific distribution, we know it is a normal distribution though. Our third major assumption is that there is some value, theta naught, which is what we're trying to estimate. In the case of a normal distribution, this is likely the mu value, or the mean. And it is defined in such a way that if we plug in the theta naught value to the family of distributions, so if we evaluate a normal distribution with that mean, we will get the density function that we don't have. So we'll be able to estimate the probability density correctly, which is the entire goal for MLE. So having these assumptions in place means that it can do what it's supposed to do. So that's a great start. And we begin by constructing the joint density function from all our observations. And so what this means is we will take our observation points, apply them into the normal distribution function, and take the product of all of those to get our density. But dealing with products, especially large products for n possible samples, is rather difficult. It's not something you want to do generally. So we take what's called the log likelihood, and we convert that large product into a large sum. Addition is a much less complex operation. Computers can do it much quicker. So dealing with sums is much, much easier. And so we take the natural log of everything, and natural log of a bunch of multiplications is the addition of the natural log of each of those individual pieces. So that's what we get here. But we can go even further, because the maximum likelihood of that probability will be, if we take the average across all of our points that we take, it'll be the largest one, or what occurs the most. It's the maximum likelihood. And so you see that definition here. So the theta hat, MLE, which is the maximum likelihood estimate for trying to approximate theta naught, is the maximum argument of the average when the likelihood is considered across all of our points. And so that's just the basic function. This is the definition we're going to be using. And it has a bunch of nice properties that go along with it. The first of which is consistency. Consistency means that as we take more and more data points, the maximum likelihood estimates will converge to the value we're trying to estimate. So if we take infinite points, we will wind up with theta not exactly. This is kind of important, because if this wasn't true, then our estimator really wouldn't work at all. So this is a good property to have. Our second major property is asymptotic normality, and it sounds a little confusing, but what it basically says is as the sample size increases, the distribution of the maximum likelihood estimate fits a Gaussian distribution with mean at theta, and covariance matrix equal to the inverse of the Fisher information matrix. Now, the Fisher information matrix is an incredibly important part of statistical analysis. We are not dealing with that for the purposes of this video, but it's just interesting to note how it's related in with MLE, and if you wind up doing work with it later, it's a very useful fact to know about your data. And the last property we have for MLE is efficiency. It's one of the reasons MLE is as popular as it is. It's, as far as I'm aware, the most popular parametric density estimation function, and that's because there is no constant estimator that has a lower mean squared error. That means this is the best you can get in terms of constant estimators, which is incredibly good. So now that we understand maximum likelihood estimation and with the properties involved with it and what it's trying to accomplish, let's look at it with regard to some sample data. So our first set of sample data is a normal distribution with mean of 1, with sigma 1, and approximated by this histogram with 1,000 data points. So we can see that there are almost 100 of those 1,000 data points at pretty much exactly around the mean. This is expected. This is what we're hoping for. This looks like a normal distribution, which, by the way, is also called a bell curve, if you're more familiar with that nomenclature than normal distribution. Anyway, we have a normal distribution. It looks like a normal distribution. If we try the maximum likelihood estimation function in MATLAB, just applied to this distribution right away, we get a nice looking bell curve. In fact, the values estimated to us from MLE are very close to what the actuals are. This is good news. This is exactly what we wanted to see. This is how it works. This is what we're trying to verify. But if it works this well, why would we even have to consider it over multiple trials? You know, you can just run it once and it's this accurate. Well, that's because you don't always have the luxury of 1,000 data points. And if you have, say, 20, it's a completely different animal. So this example, it doesn't look very much like a bell curve. It looks more like a box. And taking the normal distribution is not supposed to look like a box. The maximum likelihood estimate for this distribution still looks like a bell curve, but that's because, as mentioned in our assumptions, it's part of a family which we know is a normal distribution. So the maximum likelihood algorithm is saying, I know this is supposed to be a normal distribution, let's find the closest one. And it's not that great. Mu is 1 and sigma is 1 for this case, and our estimates are quite far off. Nowhere near as good as they were with 1,000 data points. But that's to be expected. We had 1/50th of what we're supposed to have. So the question then becomes, well, how can we get better? We know with 1,000 it's good, we know with 20 it's terrible. So let's step back even further for a moment and go to 10. But what we're going to do, instead of just estimating it once like these examples, we're going to take the estimate 50 times, and we're going to plot that and see how it looks. So that's what this plot is. The line at 1 signifies what mu actually is, and all of those blue X's are what the MLE estimates to for any given 10 points that were pulled. So we see that there's outliers with estimates at 1.8 and just under 0.4 when it's supposed to be 1. But the good news is we see that there are a lot of them around 1. In fact, if we take the average of all of these 50, that's our mu hat value in the bottom corner, it is almost exactly 1. At 10 data points, which is half of what we had at 20, which looked terrible, we got almost as good of results as when we had 1,000. Like, that's wonderful. Like, taking this average significantly increased what we can do. In fact, the confidence interval presented by the maximum likelihood function isn't even that bad either. Going to 0.97 or 1.16 to pretty much within 95% guaranteed sigma somewhere in there, or theta somewhere in there, that's huge. We had 0.6 as our previous theta hat, and now we're in perfect ballpark. It's great. We can see that if we do the trial again, the mean comes out to just under 1. So we've done two different independent trials that have roughly the same results. We have slightly worse outlier on the bottom, which might be what's dragging down mu hat, but the results are consistently clustered around what actual theta is, and that's good for us. If we examine the confidence interval, we can see that it encompasses our true value. That's exactly what we want to see. For 10 data points, taking the average of 50 trials is looking pretty good. So let's say that we can get more than 10 data points. I mean, the more we can take, the better. But how high do we have to go to actually get really good values? Like, yes, our average is coming out great for this one, but there are some problems associated with that. If we, for example, if we didn't have a normal distribution, we had some kind of other distribution that wasn't as well behaved, doing the multiple amount of trials with 10 samples, you could completely blow out of proportion some defects or different features that just aren't actually there. It's just a result of your oversampling. So let's see how many samples we actually have to take to get decent values without going to an average of 50 trials. So here's an example. We take 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100 samples, and we evaluate 50 trials at each of them just to see kind of how they're clustered around our true value. And what we see is we have the same range for 10, that's the same samples we presented before, but as we go towards 100, they get significantly better. In fact, the furthest down the 100 samples goes is not even to 0.8. So our MLE estimates look great. We took 10 times as many points, and we increased our confidence interval by about 0.2, which is by no means bad. That's quite good. But we're starting to see a trend in that it's obviously not linear that we increase sample size to increase our confidence. But there is a trend going on. Otherwise, there would be no point in doing more and more samples. So before we go on to hires, for a higher amount of samples, let's see what our means look like. And with the confidence intervals, we can see that, again, for every single one, the confidence interval includes our true value. In the graph, you can see the red outliers around the red circles are the range for the confidence interval, and all of them include our true value. That's exactly what we want to see. It means that the estimator is working properly and giving decent results. So now that we've seen this, let's go on to, say, increase it by a factor of 10 again. So we go from 10 samples to 100 samples, and now to 1,000 samples. And at 1,000 samples again, we see it's even better. So before we went from 0.85 to 0.95, and now we go from 0.95 to 0.98. So we've increased our confidence interval on the minimum side again, and same thing's true for the maximum side, just with slightly different numbers, by increasing by a factor of 10. And it's starting to look like a logarithmic kind of relationship between increasing our sample size and decreasing or increasing the accuracy towards our true value. So let's increase by a factor of 10 again. Let's go to 1,000, and instead of doing steps of 100, let's evaluate over steps of 10. It'll be harder to see the individual lines in this case, but we'll get a huge look at the trend and see how that turns out. And that's what we have here, and yes, it's definitely a logarithmic relationship. And we can see that at 10,000 samples, we almost have exceeded MATLAB's basic precision for these values. It does 4 decimal points, and we've almost exceeded that. So depending on how detailed we need it to be, this may be overkill. We may have been able to stop at 1,000, but looking at how it shrinks towards the true value, taking more samples is definitely not a bad thing, especially when you need that accuracy. So we mentioned our 3 properties for MLE. We can verify the first one right here, right away. It's definitely approaching our true value as the number of samples goes to infinity. The second one we saw with each individual sample size, how it was a Gaussian-like distribution for each 50 MLEs. So that was nice to know. And then minimum accuracy, again, that's the whole reason we're using MLE. So we verified our 3 primary properties of MLE by examining this data, which is great. But what else can we do with MLE? And it turns out quite a bit. The specific thing we're going to look at is called the Kullback-Leibler Divergence. And what that is, it is a measure of the divergence between 2 probability distributions. This sounds like it doesn't match up with MLE at all. But it turns out that the KL divergence is a measure of information lost when a distribution Q is used to approximate a distribution P. And that's exactly what we're doing with MLE. We have an unknown distribution P, and we are generating an approximation, and that becomes Q. So it turns out that this is exactly what we're doing, just worded a little differently and kind of in a different format. And in fact, it's a very different format because it's the integral of the difference between the logs. And at first, that doesn't seem like we can get there from MLE or vice versa. But it turns out we can, and it's actually rather simple. So the first thing we do is we start with our MLE function. We're taking the maximum argument of the average of the log likelihood. And what we do is we go through the real analysis axiom of if you're taking the maximum of a positive set of values, you can accomplish the same thing by taking the minimum of the negative. So the minimum of negative likelihoods is the same as the maximum of the positive likelihoods. So we make that substitution right away. And then for readability, we go ahead and we recollapse back up the probability function into the summation. So this is exactly what we had before, just with argmin and negatives instead of argmax. And so now what we can do is, okay, we're looking for the expected value of this to get rid of our summation. And we see that we're summing the natural log of the function applied to x over n terms. And then we're dividing it by n. And as might be fairly obvious, we get the expected value being the natural log of the function applied to x. So after that, we need to figure out how to get the divergence because we're down to a single term. This is the furthest we can go just evaluating maximum likelihood. But as we mentioned earlier, we need to have the true value in order to find the difference between them. So what we do is we proxy up our expectation value as the difference of our 2 probability densities, where again theta naught is the true value for theta, and f applied to theta naught is f of naught, which is the probability density that we don't have. So this is exactly the definition of the KL divergence, except now written in the form that we've been using with MLE. So what we can do from this point is we can apply the basic logarithm property of the subtraction between 2 logs is actually just the division within the logarithm. And then from here, we can apply the general definition of expected value. Since these 2 functions are based off of each other, we can take the inner product of the 2 to rewrite this expectation value as an integral. And this looks really familiar, and that's because this is the exact definition of the KL divergence, just written slightly differently. So we found the KL divergence from MLE. We can derive one from the other. That's incredibly powerful because while they are effectively the same data, they're used in very different ways because the KL divergence is used when you need to know how much information is missing. So you can apply that where you find out how much extra information you need to provide to compensate for what your approximation is missing. This is how it's mostly used, just to build up better data sets. And it's a different application than MLE, but they're derived from each other. And occasionally you'll swap back and forth. The KL divergence is also useful in other different things known by a few different names. It can also be called information divergence. It's used for information gain and relative entropy, which are other very important components of statistical analysis, and it also referred to the acronym KLIC. So what conclusions can we draw from using MLE in this manner? So the first thing is, when our sample size is low, calculating the mean of several MLE evaluations will give a much more accurate estimation of theta naught than any single estimation on its own. And that was obviously true. We saw we had better data than a single evaluation at 100 points when we had 50 at 10. But as mentioned earlier, that can result in oversampling of defects if the density function's bad. It works great for a normal distribution, and you can always apply it, but you need to take into account the fact that your probability distribution you're starting with may not be well suited for this sort of additional analysis. As we increase our sample size normally, which is always going to be useful, we saw that the confidence increases with a logarithmic relationship. So a factor of 10 increase in the sample size was a much smaller increase in the confidence, but there was still increase to increase, which is exactly what we were hoping for. It seems that between 100 and 1,000 will be 2 or 3 decimal point precision within when you're looking for the true value, and that's pretty good. And our last conclusion is converting the maximum likelihood estimator to the KL divergence presents the same information in a different manner that may prove more useful depending on the specifics of the problem. And that's kind of just a blanket statement. KL divergence is used in a lot of different ways from MLE. Sometimes you won't even care about it, but inherently it makes sense that trying to maximize the estimation of a value is the same as minimizing the difference between them. So with that, this video is complete. If you're interested in the topics covered in this, you can download the MATLAB code used to generate all of my data distributions from this Dropbox link. Additionally, there are several papers and articles that I got my information from when writing this that are referenced here. This slideshow is available on Dropbox as well if you're interested in going back through this again later. But thank you very much for watching, and I hope you learned something.